So here we have a homemade dynamometer. So starting in the back, we have, back here we have an electric motor in a clear plastic box. And then over here, we have a wheel here that has a little magnet in it. So we could use the Hall effect sensor here to measure the speed. Then this is called a prony brake, this piece over here. And essentially I've got some, behind the wheel here, I've got some cork in here. This acts as a brake. And as I tighten, there's a screw in here, and as I tighten that down, it'll put more and more force on the shaft. And then through this arm, it transfers into the load cell. So I'll get the load cell force, and I know this is a 45 millimeter moment arm, and from there I can get the torque. So that's the mechanical output. And here I have this is the load cell chip here, the HX711, which some of you have used in sensor class. And then both of you have used the current monitoring chip, ACS712, and used a voltage divider here to measure voltage. So I have voltage, current, force, which is torque, and then speed. So I'm going to turn this on. Keep in mind, this is a 12 volt, 30 watt motor, which means it should be able to handle up to 2.5 amps. And actually that's the rated current, so it could actually go more. Unfortunately, my power supply only goes up to 1 amp. So I'm not sure how many readings we're gonna get. So we'll just start up and see what happens. Here is a close-up view in isolation of my little prony. Okay, so this is a prony brake. And I want to emphasize, it's a prony brake. Some people call it a pony brake, but this French mathematician and engineer, Gaspard de Prony, is responsible for it. So it's a prony brake. And what it is that you would squeeze the shaft with the cork material. See, because I'm in Italy where the vino's all over the place, but cork material is also very good for this kind of application. Had I used another 3D printed plastic, these things would kind of just weld together and it'd be melting. So cork was a very good brake material for this. And you see these two upper lower parts are held together with screws. And essentially when you tighten the screws, you just essentially apply more brake force to the shaft. And as you see here, the point here is what goes and presses on the load cell. So from that, you could figure out what the torque is that is coming from the shaft. Okay, we've got our motor running with minimal load on it. And now we're going to start putting some more load on it. If you listen carefully, you could hear a slight change in pitch of the motor. Tighten the screws to keep putting some more and more friction on the spinning shaft. I'm alternating back and forth between the two holes to more or less keep the gap between them parallel. You can hear the motor slowing down as we are squeezing on it more. At some point, we'll get it to stop. And now we've hit that mark. So here's the data that we captured during the run. So what I did here was I took out all of the points where I was adjusting it, so all the rough spots. So basically, it just every time it was running without any sort of intervention. So you see the data here, it starts at a speed of about 1800 RPMs, and we went down to about, where did it end up? Yeah, around 1300 or so when it quit. So you see where it gave up pretty quickly. This is a very minimal power supply, especially for this type of motor. So you're going to see the data is not great. For instance, I was trying to give it 12 volts, and you see we didn't get past 9.3 volts. And the amps were about 1, and it went down. Actually went a little up from there. And you see the amounts of torque in Newton meters, which Newton meters is a very large measure, are also pretty low. So what can we do with this data? Well, one thing we do is get what's called the kV and kT of the motor. So the definition of kV is the RPMs per volt at no load. So we take the least load possible, which was the first one. I took all those data points and we averaged them, just dividing the speed divided by the volts. It came up to about 200 RPMs per volt. Then the other measure of a motor is called the KT, which is the torque per amps, torque per current. And so what I did here was I created a linear regression. I plotted the torque as the vertical axis and current as the horizontal, and you end up seeing that it comes out on this sort of straight line, and did a linear regression and end up getting 0.0277 Newton meters per amp. So that's if you're interested in KT and KV. So let's look at the mechanical output. So we see here we have the torque is linearly decreasing as we expect, and the power, as it turns out, follows a quadratic, like a parabola. So what do we figure out from here? Well, we do a linear regression between the torque and the speed, and we get the curve and we get our limits here. So when the speed goes to 0, that would be called the stall torque. So that comes out to be the y-intercept, which is 0.048 Newton meters. And on the other hand, if we extend it out to where it crosses the x-axis, that is, hits a value of 0 torque, we're going to guess the no-load speed is around 2,042 RPM. So that's pretty close to what we observed. So notice that's that value. Then looking to the power curve, we're going to see where is the spot where we expect power to hit a maximum and at what speed. And in this case, we didn't get down to a power of, we didn't get down to a speed of 1,000. It quit at about a little under 1,300 actually. But had we been able to get down to there, we could have gotten as much as 2.6 watts of power. Let's quickly look at the electrical input. I'll go to here, this tab here. And one thing I do want you to notice is that the voltage actually decreased as the speed decreased. Now this is not good. This is, if we had a good, strong power supply, it would supply the correct amount of voltage at all times. So unfortunately, this power supply was challenged and it couldn't hold up. So that's why you see the voltage is going down as the speed goes down. That is, as we're applying more load to it. You can see as the speed goes down, the torque the current actually increases. So the power is increasing as you're going from no load. From no load to load where it stalls, where it actually stalls. This brings us to the overall efficiency, which would be the mechanical power we get out divided by the electrical power we put in. And you see this This isn't very good, 8%, and we look at it's also a parabolic curve, conforms to a quadratic law, and so we can predict where the maximum would be and where the zeros would be by solving the quadratic equation. So anyway, it predicted that the maximum efficiency would have occurred at 1200 RPM, and we would hit a peak of 18%. And using this curve, we see that it would predict that it would go down to zero efficiency at about 340 RPM, which we're hoping it would have been closer to zero. But the high would be 2071, which actually agrees pretty well with what we would predicted for the no load speed, 2042. Compared to 2071, that's pretty close for this kind of measurement. So that's what we do with dynamometer measurements. And at this point, you would decide what application this motor would be good for.